So in section 9.5 and 9.6, we're going to be talking about solving exponential logarithmic equations. So we're still hitting SLL number 2. So we'll be applying the change of base formula. We're going to apply the concepts related to exponential and logarithmic functions, solve applications involving exponential equations, solve logarithmic equations, and solve applications involving logarithmics. So the first thing we need to do is introduce the change of base formula. Let a, b, and m be positive real numbers such that a and b do not equal 1. Then we can find log base b of m by following. Log base b of m equals log base a of m over log base a of b. Or more specifically, log base b of m equals the common log of m over common log of b. Or you could also use the natural log of m over natural log of b. So for example, if I had log base 5 of 10 to the third, my change of base form allows me to write as the natural log of 10.3 over the natural log of 5. And then, even though I can't put that in my calculator, I can put this in my calculator. And so if I do my fraction key, ln 10.3, and then ln 5 on the bottom, gives me 1.449. So if I round it off to 3 decimal places, that would be my answer. This now is just a reminder when we're doing this. When you're working with the domain of log functions, remember that domain is equal to the positive real number. So for the logarithmic function to be defined, the argument has to be greater than 0. That means when solving logarithmic equations, we need to check all potential solutions to be sure the solution does not make the original equation undefined. In this section, we're going to be using the following tools to help us solve exponential and logarithmic functions. Now before we do that, I want you to take a minute on your calculator. And I don't care if you use natural log or common log. If I try to take the common log of 0, I get a domain error. If I try to take the common log of -1, I'm going to get domain error because the logarithmic functions are only defined when the argument is positive. So here are our tools. B to the x is 1 to 1. And we've talked about this before. Let u and v be real numbers, b greater than 0 and b not equal to 1, then u equals v if and only if b to the u equals b to the v. So if I can write them with the same base, I can set the exponents equal to each other and solve. We have our definition of log function we've used before. Y equals f of x equals log base b of x if and only if x equals b to the y. So power equals log base of argument if and only if the argument equals base to a power. We have a tool that log functions 1 to 1. Let m, n, and b be positive real numbers, b not equal 1. Then m equals n if and only if log base b of m equals log base b of n. So we can set the arguments equal to each other. And then we have our properties or laws of logs. The product rule, the quotient rule, and the power rule that we talked about before. So let's kind of see this in action. So here on this first set of problems, we want to use the fact that the log function's 1 to 1. In order to make this work, we're going to have to rewrite them so they have the same base. So I look at 125 and I want to see if I can write that as a power of 5. Well, if I do 5 times 5 is 25. Times 5 is 125. So I'm going to need 3 of those. So I'm going to leave this side alone. But I'm going to rewrite this as 5 to the third power. Now I'm going to use this property that my exponential function's 1 to 1. See, I can't do it here. So let me not circle that. My bad. But I can do it here. I can set that 3x minus 1 equal to 3. Because So I'm using the fact that exponential functions are one-to-one. And now I'm just going to solve for x. I'm going to add 1 to both sides. And then I'm going to divide by 3. And so that's my answer. Now, nice thing, since exponential functions, their domain's all real numbers, I don't need to check this. Now I can. I could go here and do 5 caret 3 parentheses, fraction key 4/3, close parentheses, minus 1. Hit enter. It does give me 125. Well, let's try this next one. And here I've got a 1/4, and I have an 8. Well, 4 and 8 are powers of 2, so I want to write this in terms of 2. So this 1/4 is 1 over 2 squared. And remember, to bring it up into numerator, I can change the sign of the exponent, 2 to the negative 2. 8 here is 2 times 2 times 2 is 2 to the third. Power raised by power, I multiply the exponents. So that tells me 2 to the negative 2 equals 2 to the 3x. And now I'm going to use that as 1-to-1. My bases here are the same. So I'm going to set those equal to each other and solve. And this one's pretty easy to solve. I'm going to divide both sides by 3. So that gives me x equals 2/3. Now again, if I want, I can check this on my calculator. So when I would do that, I would take my 8, do my caret key, my negative sign next to the enter key, fraction key, 2 over 3. Hit my right arrow key a couple times to get out. Notice I get 1/4. So it does check. And now we want to apply the change of base formula to solve these equations. So here's what we do. If I got an exponential equation, I need to solve for the exponent. I'm going to need to use the definition of logs, rewrite as a log equation, and then do my change of base. So I'm going to rewrite this as x equals log base 2 of 7. Changing it from exponential log form. Now use your change of base. And I'm going to use the common log. Log of 7 over common log of 2. So I'm going to go in here on my calculator, put a fraction key, log of 7. Make sure you close the parentheses. Log 2, close the parentheses. Hit enter. And they want 4 decimal places, so we'll do 2.8074. So let's try this one. So again, immediately going to go change into log form. So this would be log base 3 of 0.07. And I'm going to use my change of base here. So this would be log of 0.07 over log of 3. And I always remember this, that the b is always written lower here, so it's got to go on the bottom here. So this would be 0.02x, and I'm going to stick that number into our calculator. So let me slide this over. fraction key log of 0.07 over log of 3. Hit enter. So that's a negative 2.42 blah blah blah. I'm going to leave that answer in a calculator. Keep in mind, I could also use natural logs. If I took, for example, if I did natural log of 0.07 over natural log of 3, I'm going to get the same answer. So you're just pick one. Just pick common log or natural log and just run with that one. Now to solve this, I need to divide this by negative 0.02. So I'm just going to hit my division key, put my negative 0.0. Oops, something went wrong. So let me try that again. Clear that out. I'm going to divide negative 0.02. Make the calculator do all the work. And so that would give me x is approximately 121.0281. So now we've worked these and we have a way to address the original question we started back in section 9.3. So remember 9.3, this is where all the logarithms started because we were trying to solve for the x equals 13. You now can solve that problem. It's going to work exactly like these. So in fact, let's do that as an exercise. I'm going to go and find a little spot up here. So if I have 4x equals 13, rewrite that as log form. X equals log base 4 of 13, and then use your change of base. And see, now we're able to get that answer. Took us a while to get there, but we've now gotten there. And there it is. 1.8502. So, by the way, this is called an approximation. And this is what the book calls the exact form.